Welcome back to the deep dive. Today, we are putting a piece of hardware on the operating table that is, I think, widely considered a masterclass in embedded systems design.
Oh, absolutely.
We are popping the hood on the BeagleBone Black.
This is a board that really, it separates the casual hobbyists from the systems engineers. We live in this world of black boxes.
Right.
You buy a computer, a phone, even a microcontroller, and it's usually wrapped in all these layers of abstraction. They're designed to keep you away from the hardware.
And the BeagleBone Black, or the BBB as everyone calls it, is the complete opposite of that.
It's the anti-black box. It invites you in.
The sources we're looking at today all describe it as a bridge. And I think that's a perfect place to start our mission, a bridge between what and what.
Between the two dominant worlds of computing. On one side, you've got the microcontroller world.
Like an Arduino.
Exactly. Think Arduino. It's simple, it's raw, it controls electricity directly. But, functionally, it's pretty limited. It can't easily run a web server or process video or manage a complex file system.
And the other side.
That's the microprocessor world. So your laptop, a standard desktop, it runs Linux, it's smart, it has file systems and networking.
But it's totally detached from the physical world.
It is. It's detached by these massive layers of software. And the BeagleBone Black sits precisely in the middle of those two worlds.
So it's a true hybrid system.
That's the word. It really demands that you understand it as a complete system. It offers the, let's say, high-level brains of a Linux operating system.
But with the low-level reflexes of a microcontroller.
You nail it. And the real reason we're doing this deep dive, the reason this board is so special, is because of a very specific architectural feature. It's a kind of secret weapon.
Ah, you're talking about the PRUs.
Ah.
The programmable real-time units.
That's the magic trick right there. But before we get to the magic, we have to understand the philosophy. Why build a board this way in the first place?
Well, the notes mention direct hardware exposure. That phrase alone sounds a little bit intimidating for someone who's just used to writing, say, Python scripts or working with high-level APIs.
It can be, sure, but it's necessary for control. If you're building a robot arm or a drone or an industrial sensor network, you just can't afford abstraction.
Can't have delays.
You can't. You can't afford to have the operating system say, hold on, I need to update a log file right at the exact moment your motor needs a start signal.
And the BeagleBone Black is designed to give you that deterministic control.
Deterministic control. That means when you tell it to jump, it jumps at that exact microsecond every single time, without fail.
Okay, so let's strip this down. Section 1, the core philosophy. We're calling it the best of both worlds. How does that actually manifest when you plug it in?
Well, when you power it up, it just looks like a computer. It boots a full Linux distribution, usually Debian.
So you get a command line.
You get a shell, you have SSH access, you can install packages with apt-get, just like on a server. You can run Python, Node.js, C++, Scilab, even Java. That's the computer side of the coin.
And that makes it really accessible, right? You don't need a specialized programmer dongle or some proprietary compiler just to get a Hello World running.
Not at all. But, and this is the key, unlike a desktop, the architecture doesn't hide the messy bits of the hardware.
Yeah, the source material really highlights that contrast.
It's a huge contrast. On a desktop, if you want to blink an LED, you might have to go through a USB driver, the kernel's USB stack, a bus controller. It's like playing a game of telephone with the electrons.
And on the BeagleBone?
On the BeagleBone Black, the architecture maps the physical pins, the GPIOs, directly into the memory space of the processor.
What does that mean in practice?
It means you can literally write a 1 or a 0 to a specific memory address, and a physical pin on the board turns on or off instantly.
So that's the microcontroller side bleeding through into the operating system.
Precisely. And that hybrid nature, that's what dictates the use cases we see in all the research. If you just want to browse the web, this is not the tool for you.
But if you want to do something like sensor fusion?
Yes. If you want to take data from an accelerometer, a gyroscope, and a GPS, do some heavy math on it with a Linux library, and then fire motors to balance a robot, this is the architecture you need.
High-level math in the front, low-level muscle in the back.
That is a great way to put it. A really great way.
Let's look at the brain then, the thing that makes all this possible. Section 2, the TI Satara AM3358.
The system on chip. And that terminology, is really important here. It's not just a processor.
Right. It's a full system.
It is.
I'm looking at the spec sheet here. It's centered around an ARM Cortex-A8 processor running at 1 gigahertz. Now, for our listeners who track specs, 1 gigahertz might sound, a little modest compared to a 4 gigahertz desktop chip.
It might. But in the embedded world, that is a powerhouse.
Why is that?
Because in the embedded context, things like efficiency and pipeline management matter a lot more than just raw clock speed. The Cortex-A8 is the manager. Its job is to run the Linux kernel and manage all the traffic.
And it has a superscalar pipeline.
Which means it can actually execute more than one instruction per clock cycle under the right conditions. It's highly optimized for handling a real operating system.
The notes also call out a specific component, the MMU, a memory management unit. Why is that so important in the architecture?
The MMU is the gatekeeper. It is the component that allows for virtual memory. This is the distinct line that separates a real computer from a simple microcontroller.
And it gives you memory protection.
Exactly. It lets the system protect memory spaces. So if your web server application crashes, it doesn't take down the kernel.
Or the motor control.
Or the motor controller. If your Python script has a memory leak, the MMU contains it. It provides the stability you absolutely need for long-term deployments, like in a factory or a remote weather station.
But the AM3358 isn't just a Cortex-A8. This is a system on chip, which means there are other distinct processors living on that same piece of silicon. The notes call them accelerators.
Right. If the Cortex-A8 is the general, these are the specialists. First up, you've got the Neon SIMD unit.
SIMD. That's single instruction, multiple data. Can we unpack what that actually means for performance?
Sure. Imagine you have a long array of audio samples, and you want to increase the volume. That's just a multiplication problem. A normal CPU does it one by one. Sample A times 2, then sample B times 2, then sample C.
Sequentially.
Right. The Neon unit grabs a whole chunk of data, say 4 8 samples at once, and multiplies all of them in a single tick of the clock.
So it's a massive speed boost for things like signal processing.
Signal processing, cryptography, simple graphics math, it's a huge boost. So even though the clock speed is 1 gigahertz, the throughput for these specific vector tasks is much, much higher because it's doing work in parallel.
Got it. And then there's the GPU.
Yep. The PowerVR SGX 530. A real GPU on an embedded board.
And it supports OpenGL.
OpenGL, yes, yeah. This allows the board to drive a display and handle the frame buffer without the main CPU having to calculate every single pixel change. It offloads all that visual heavy lifting.
So the theme here is just integration. You don't need a separate graphics card or separate math coprocessor or a separate I/O controller.
It's all baked right into that one black square in the middle of the board.
Which is how they keep the form factor so incredibly small.
Literally the size of a credit card.
All right, we've established the capabilities of the manager. But now we have to talk about the real star of the show. Section 3, the secret weapon, the PRUs.
The programmable real-time units. This is the feature that I think gives the BeagleBone Black its legendary status in the engineering community.
Okay, so physically, what are we looking at?
Deep inside that AM3358 silicon, sitting right next to the main CPU but electrically separate, are 2 additional 32-bit RISC cores.
Okay.
And they run at 200 megahertz.
Now, a listener might hear 200 megahertz and think, that sounds slow. But you're shaking your head.
It's not about speed, it's about determinism. This is the single most important concept in this entire deep dive.
Okay, define determinism for us in this context.
All right. Imagine you have a stopwatch, and you want to press the button exactly every 10 seconds. If you're doing that while you're also cooking dinner, answering the phone, and watching TV, you're going to be late on the button press sometimes.
You have jitter.
You have jitter. That's Linux. Linux is multitasking. It cannot promise exact timing because it might be servicing an interrupt from the Ethernet port right when you need to flip a switch.
And the PRUs.
The PRUs are like a monk in a silent room with nothing but the stopwatch. They don't run an operating system. They have no background tasks. They just execute instructions in a perfectly predictable sequence. Each instruction takes exactly 5 nanoseconds. No more, no less.
So if I need to send a signal to a motor every 5 microseconds, the PRU can do that. Perfectly. Forever.
Yes. And the brilliance of the architecture is that these PRUs have their own data bus. They can talk directly to the GPIO pins without asking the main CPU for permission.
They bypass the manager entirely.
They bypass the manager, which brings us back to that hybrid model again.
It does. How does that play out in a real project?
Okay, so you write your complex logic in Python or C++ on the main Linux CPU. You say, calculate the path for the robot arm based on the camera input. Then you pass that target coordinate to the PRU through shared memory.
And the PRU takes over from there.
The PRU takes that target and just handles the high-speed, precise electrical pulses to actually move the motors. That's its only job.
It's like a conductor and a percussionist. The conductor, Linux, decides the tempo on the song. The percussionist, the PRU, actually hits the drum with perfect rhythm.
That's a fantastic analogy. The conductor doesn't have to hit the drum themselves.
And that opens up capabilities that are usually impossible on a computer this size.
Yeah.
Like you can bit bang protocols. That's a term that comes up a lot in the sources.
Bit banging, yeah. It means creating a communication protocol just by turning a pin on and off very, very rapidly in software.
Normally, you'd need a dedicated hardware chip for that.
Usually, yeah. To run protocols like UART or SPI or DMX for stage lighting, you need a special chip. With the PRUs, you can just write software that toggles the pins so fast and so precisely that it becomes the hardware interface.
So the BeagleBone Black can effectively change its own hardware capabilities on the fly.
That's it. That explains why this board is found in so many industrial controllers and high-end 3D printers. It's not just a computer, it's a programmable timing generator.
If you need hard real-time performance.
Meaning, if missing a deadline results in a system failure,
You need the PRUs.
you need the PRUs. It's a capability that puts the BBB in a league of its own, really.
Let's move to section 4. The nervous system. We've got the brains. Now, how does it actually touch the world? We're talking about the headers, P8 and P9.
The famous double rows of pins, 46 pins on each side.
So that's 92 pins total.
Yep, giving you access to about 65 GPIOs, general purpose input-outputs.
65 is a massive number compared to the standard 40 you see on most consumer boards. But there's a catch, right? A big, complex catch called pin multiplexing.
They're pinmucks, yeah. This is the hurdle where a lot of beginners trip and fall, but it's also where all the flexibility comes from.
So walk us through it. What is it?
Okay, so the chip inside, the AM33358, supports a huge number of interfaces. Multiple LCD drivers, multiple SPI buses, UARTs, timers, PWMs, all sorts of things.
Way more things than there are physical pins.
Exactly. If you counted up every single signal the chip could generate, you'd need hundreds of pins coming out of the plastic package. That would make the chip huge and expensive.
So they have to share the pin.
They share. Every physical pin on the header is connected to a selector inside the chip, and that selector can choose one of up to, say, 7 or 8 different functions for that single pin.
So pin 20 could be a generic digital switch today, but I could reconfigure it to be part of a video display tomorrow.
Precisely. But, and here's the friction, you can't use all the functions at once. It's a zero-sum game. If you turn on the HDMI display, for example, it consumes a whole bunch of pins.
And those pins are then unavailable for anything else.
Right. If you want to use those same physical pins to control motors instead, you have to disable the HDMI in the software configuration. You're constantly trading off capabilities based on your project's needs.
And this whole configuration is controlled by the device tree.
The device tree. It's a data structure. It's essentially a map that loads when the OS boots up, and it tells the Linux kernel, hey, at this memory address, I have enabled a serial port, and it is using pin 15 and pin 16.
And if that map doesn't match what you've physically plugged in,
Nothing works. It's like manual wiring, but you're doing it in code.
it forces you to be very intentional. On a plug-and-play system, like a Mac or Windows PC, you just plug in a mouse, and it works.
Right. But on the BeagleBone, you have to tell the kernel, I'm about to plug in a mouse, and here's exactly how the electrons are going to flow. It's just a deeper level of engagement with the system.
Let's list some of these interfaces, because
Yeah.
the variety is what makes the board so versatile. We have the standard serial interfaces, UART, SPI, I2C.
Bread and butter for sensors. That's how you talk to temperature sensors, gyroscopes, small displays, things like that.
But then we have CAN bus. The notes emphasize this heavily as a differentiator.
CAN controller area network. This is the language of automobiles and factories. Your car's engine talks to the brakes and the dashboard over CAN.
And the BeagleBone has native CAN controllers built in.
Directly into the hardware. You just need a cheap little transceiver chip to convert the voltage levels, and suddenly this board can listen to your car's engine diagnostics or control a massive industrial conveyor belt.
That is a clear differentiator from consumer boards, which almost never support CAN natively. And then there are the analog inputs.
The ADC, the analog to digital converter. Most digital chips, they only see ones and zeros. But the real world is analog temperature, pressure, light levels, sound.
And the BBB has 7 channels of 12-bit ADC.
Meaning it can measure voltage with 4,096 steps of precision.
So instead of just hot or cold, you get 25.43 degrees.
Exactly. And it's integrated right into the board, accessed via the industrial I/O subsystem in Linux. You don't need to buy an external breakout board just to read a potentiometer.
And finally, networking in USB. We have the Ethernet jack, which is standard, but the USB client, the mini USB, does something really clever.
Oh, it's a feature I wish every single board had. When you plug the BeagleBone into your laptop via USB, just for power, it doesn't just charge, it acts as a USB gadget.
It emulates a network adapter.
Yes, it creates a virtual Ethernet cable over USB. Your laptop sees a new network connection. You can ping the board, SSH into it, access its web server, all through the power cable.
So no hunting for IP addresses on your router.
No Wi-Fi passwords to type, no messing with network settings. It drastically lowers the time to hello world. It's brilliant.
Moving on to Section 5, Memory and Storage Architecture. We have to talk about constraints here. The board has 512 megabytes of RAM.
DDR3L SDRAM, yep. And yes, in a world of 16 gigabyte laptops, 512 megs sounds tiny.
Is it a bottleneck?
Well, it depends entirely on your mindset. If you try to run a heavy desktop environment with a graphical browser and 5 tabs open,
It's going to struggle.
it will struggle. It'll thrash the swap file. But for an embedded system, a headless controller running code to manage a machine 512 megabytes is an ocean of memory. It forces you to be efficient. It forces you to write better code.
Constraints breed creativity. Now, for storage, we have a dual-path system. There's eMMC and a microSD slot. Why both?
This is a critical architectural decision for reliability. SD cards are great for cameras, but they can be problematic for operating systems.
How so?
Well, they can vibrate loose in industrial settings, the contacts can oxidize, and they're generally slower. The BeagleBone Black has 4 gigabytes of eMMC that's embedded multimedia controller soldered directly to the board.
So it's basically a soldered-down SD card, but better.
Much better. It uses an 8-bit wide data bus instead of the 4-bit bus on an SD card, so it offers higher throughput. And because it's soldered, it's vibration-proof. This is your production drive.
So the intended workflow is develop up on the SD card, experiment, break things, fix them. And then when you're happy, you flash that final image to the internal eMMC for deployment.
That's the workflow exactly. And if you happen to brick the eMMC, if you mess up the configuration so bad it won't boot, you just pop in an SD card, hold down the boot button, and the board boots from the card.
So it has a built-in safety net.
It makes the board very, very difficult to permanently break.
Speaking of booting, the sources give us a deep dive within a deep dive on the boot process. It's not just hitting a power button, is it? There's a whole relay race happening.
It's a fascinating sequence, and understanding it is critical for debugging. It all starts with the ROM. This is code that's hard burned into the silicon at the factory. It wakes up and just looks for a boot device, MMC0, MMC1, UART, USB.
Okay, then it passes the baton to the SPL.
The secondary program loader. See, the internal RAM, the SRAM inside the CPU is tiny. It's only about 109 kilobytes. The main 512 megs of DDR RAM isn't even turned on yet because the memory controller hasn't been initialized.
Right.
So the ROM loads this tiny program, the SPL, into that tiny internal cache. And the SPL's only job is to initialize the memory controller and turn on the main RAM.
So it's the starter motor for the main engine.
That's a perfect analogy. Once the big RAM is online, the SPL then loads U-boot.
U-boot, the universal bootloader.
This is Grand Central Station. U-boot is incredibly powerful. It has its own command line. It's the thing that loads the Linux kernel and that device tree we talked about earlier. It passes the whole hardware description to the kernel.
And then the kernel takes over, mounts the file system, and finally, user space.
And your system services start. And the reason you need to know this is if your board doesn't boot, you need to see where it stopped in that chain.
Did the power LED come on? That's a hardware problem.
Right. Did you get text on the serial console? That means SPL and U-boot are alive? Did it hang while loading drivers? That's a kernel issue. The boot logs tell the story.
Section 6, power and physical design. Getting into the real nuts and bolts here. Powering the board. We have the barrel jack and the USB port. The sources are very specific about this. Use the barrel jack. Why is that?
Physics. Plain and simple. The board runs on 5 volts. A standard computer USB port is limited to 500 milliamps, which is half an amp.
And that's 2.5 watts of power.
Right. The BeagleBone Black idles well below that.
No.
But if you start the CPU crunching numbers, turn on the HDMI, and plug in a Wi-Fi dongle, you can easily spike above 500 milliamps.
And what happens then?
The voltage sags. The PMIC, the Power Management IC, it's a TPS 65217C. It detects that dip and it cuts power to protect the chip. The board just reboots.
A brownout.
We call it a brownout, and it is the #1 cause of weird behavior reported by users. The barrel jack connects to a dedicated 5-volt rail that can handle 2 or 3 amps. It's rock solid.
So if you want stability, plug it into the wall.
Always, every time.
And what about physical considerations? We're talking about high-speed signals here.
This is where the architecture meets the messy real world. You have signals like SPI running at dozens of megahertz. You have edges rising in nanoseconds.
And if you use long wires.
If you connect that to a messy breadboard with long loopy wires, you've just created antennas. You get noise, you get crosstalk, the signal degrades.
So the data gets corrupted.
Right. The source material really emphasizes that for any high-speed I/O, you need short, shielded connections. And you have to respect the ground. Every signal needs a return path. If you don't connect the grounds between your external motor driver and the BeagleBone, nothing works.
Or worse, you let the magic smoke out.
Or you let the magic smoke out.
All right, Section 7, the software ecosystem. We know it runs Linux, but it's not just a generic install.
No, not at all. Historically, it ran Angstrom, which was a bit complex, but now the standard is Debian. It's stable, it has a huge repository of software, and it's very familiar to anyone who's used Ubuntu.
But the unique part is the out-of-box experience.
Yes, this goes back to that USB gadget mode we talked about. The board actually ships with a web server running on the board. When you connect, you can open a browser and navigate to the board's IP address. And right there, running inside your browser, is an IDE called Cloud9.
Wait. The development environment is hosted on the device you are programming.
Yes. You don't need to install VS Code or Eclipse or anything on your laptop. You just open Chrome or Firefox. You can write code right in the browser, hit a run button, and it executes on the board.
That's incredible for education. It just removes all that setup friction.
It's a huge barrier removed. And for controlling the hardware from the environment, there's BoneScript.
Which is a Node.js library.
It is. It makes hardware control look like web development. Pin mode, P813, LUTPU, digital write, P813, HIGH. It abstracts away all the complexity of the file system writes we were talking about earlier.
But for the serious engineers listening, you're not stuck with JavaScript.
Oh, absolutely not. No. The pros are using C or C++E. There's a library called LibreBot Control that was developed at UCSD specifically for this board. It taps into the PRUs, it handles the pin muxing, and it gives you these high-performance robotics functions.
And of course, since it's Linux, you can run Python, Rust, Go.
Whatever you want.
All right, we've covered the philosophy, the brain, the secret weapon, the body, and the software. Now it is time for the verdict. Section 8. We have to address the inevitable comparison, the BeagleBone Black versus the Raspberry Pi.
The classic showdown. It always comes up.
The source material is very clear on this. This is not a popularity contest, it's a job interview. Which candidate is right for which job?
Let's look at the specs objectively. If what you want is raw CPU power, the Raspberry Pi series wins, hands down. A modern Pi has 4 cores, it runs at much higher clock speeds, and it has gigabytes of RAM.
So if you want to build a retro gaming console or a media center,
or a desktop replacement, the Pi is the correct choice. The BeagleBone Black is not optimized for multimedia or that kind of raw number crunching throughput.
But
if you care about I/O density and determinism, the BeagleBone Black has the superior architecture.
Let's break that down. I/O density.
The Pi typically exposes 40 pins. The BeagleBone exposes 65. The Pi has practically no analog inputs. You almost always need external chips for that. The BeagleBone has 7 built right in.
And the killer feature?
The killer is the PRU. The Raspberry Pi has no real-time subsystem. None. It relies entirely on the Linux kernel for timing.
So if you're building a drone flight controller,
you want the BeagleBone. You absolutely need that sub-millisecond precision to adjust the motors to keep the drone stable in the wind. Linux on a Pi might hiccup for 10 milliseconds while it does some housekeeping, and your drone flips over.
But the PRU on the BeagleBone will hold that loop steady no matter what Linux is doing.
No matter what. So the decision matrix is clear. Media and general computing, get a Pi. Interaction with the physical world, robotics, industrial automation, get a BeagleBone.
And there's one more sort of soft factor you mentioned, learning.
Yeah, this is a big one for me. The Raspberry Pi ecosystem makes things very easy. And that's great. but it hides a lot of the complexity.
Whereas the BeagleBone Black
Right.
forces you to confront the architecture.
It does. You have to learn about device trees. You have to learn about voltage levels. It's the 3.3 volt logic, by the way. Don't plug in 5 volts. You have to understand the boot sequence. It is a steeper learning curve, but climbing it makes you a better engineer.
It's the difference between driving a car with an automatic transmission and lane assist versus driving a manual transmission track car.
That's it. You feel the road more with the BeagleBone.
And sometimes you need to feel the road to drive the perfect lap.
Precisely.
So what does this all mean for us? We've taken this deep dive into a board that is essentially a highly integrated Linux box with a microcontroller's heart.
It really represents a philosophy of transparency. In an age where everything is moving to the cloud, where APIs hide everything, where hardware is sealed shut, the BeagleBone Black just says, here is the metal, here are the pins, here is the memory map, you have total control, now go build something real.
It empowers the user to stop just consuming technology and actually start engineering it.
It really, really does.
Before we sign off, I wanted to leave our listeners with a thought. We talked a lot about those PRUs, those 2 extra brains inside the chip that run independently of the main OS, focus purely on their task, undisturbed by the chaos of the system manager.
The secret weapon.
Right. Think about that architecture, but applied to you. If you had 2 independent real-time cores in your own brain that could execute tasks perfectly without getting distracted by the main operating system of your daily life, the emails, the notifications, the stress, what would you offload to them? What complex problem would you solve if you had guaranteed jitter-free focus?
Wow. That is a dangerous question. I think I would probably offload my email checking just so my main processor could finally get some creative work done.
I would offload remembering where I put my keys. Listeners, think about your own hybrid architecture. Thanks for diving in with us today.
See you on the next layer down.
Goodbye, everyone.